Now, a disclaimer. In a traditional mathematical course on linear algebra, a more abstract course, we would take a more abstract approach. So we wouldn't define vectors as sequences or functions. Instead, we would define a vector space to be any set that came along with an addition operation and a scalar multiplication operation, any set that satisfied certain axioms and satisfied properties v1, v2, and v3. This approach has its advantages. Anytime you give a more abstract definition of something, you don't have to be concerned with the internal structure or details of the thing. In this case, we don't have to be concerned. If we took this approach, we wouldn't have to be concerned with the internal structure of vectors. This is analogous to encapsulation or information hiding in object-oriented programming. The advantage is it's more general. Now, I didn't take this approach. I took a less abstract approach for this course because I think in developing intuition about vectors, it's helpful to have this concrete representation. Now, much earlier we saw that the u to v line segment could be represented in this way. It's the set of linear combinations alpha u plus beta v, where alpha and beta are non-negative and sum to 1. We say a linear combination of vectors v1 through vn is a convex combination if the coefficients all are non-negative and they sum to 1. For example, the convex hull of a single vector is a point. The convex hull of 2 vectors is generally a line segment, and the convex hull of 3 vectors is a triangle. So you would think that the more vectors you have, the higher dimensional the object. That's not always true. For example, if these 3 points are collinear, they're in the same line, then their convex hull is a line segment. Similarly, if you have a bunch of points and they're all in the same plane, then their convex hull forms a polygon.